Okay. So I think I'm recording, right? So, okay. Uh, so I guess I am going to talk about SVM today, like support vector machine. Oh, oops, what did I click? Yeah. Support vector machine. So, by the way, you can think of support vector machine as just a single neuron network. So it's the same as like what we talked about last time. Like, oh, by the way, I guess I didn't even emphasize that like we have that term like logistic regression. Of course, it's written on the notes. So it's basically we do classification like binary classification. If you remember, like maybe I have a um, vector input. I'm going to classify this maybe okay. Okay, let's say I have an image first. Maybe I vectorize that into a vector. Then I go for a logistic regression. Basically, it's just a linear um, multiplied by a linear vector here. Let's say this is x. Let's say I have a multiplied by a, so I get ax here, and then I have a logistic function. Let's say sigma ax. This function is basically map stuff the whole x-axis into like 0 and 1 values. So the larger the ax is, the sigma will be, I mean, the output of this sigma will be larger as well. So you can interpret this as some kind of probability of the outcome. So for example, I'm trying to classify this as cat or no cat. So then the probability will be, I mean, the output will be the probability whether it's a cat or not a cat. And and by the way, this is called logistic regression because I have a logistic function here. And this basically, the name of this method is kind of a little bit misleading because you are really solving a classification problem, but because you are regressing, like you can think of, yeah, using logistic function and do regression like fitting, like a fancy word for fitting, fitting a logistic function. So therefore call it logistic regression. So, but if you kind of like kind of visualize the whole scheme here, it's nothing but it's like basically doing the same thing as I have like some data point in high dimension. Of course, I can only draw 2Ds here. So what we are trying to do is like, let's say this is like the data point like in, this is like the X space here. The domain is X. Okay, maybe I have told you. So the in this case a 2D. So like my input is like just X here. So and like I have like different points here correspond to like different instance of X. And and like this dot here is one class. Maybe this is the cat class here, right? And this is like the log cat class here, the long cat class here. Now, what we are doing here, like on the logistic regression, is actually basically we want to try to find this A here. So A is just a more or less a vector along, let's say, maybe I use a different color. Potentially, I can have a something like this. Let's say this is A here. And now, what's AX? Maybe a better way to write it will be like, maybe instead of like write AX, I emphasize this is the inner product between A and X. So should give me a binary, sorry, a scalar outcome. So it's really a projection of X uh, on along the A direction, right? And this projection will get, in this case, oops, that's very hard to draw a straight line. Suppose I draw a straight line. Let's try. Yeah, let's see what happened here. Did I? Oh, okay, that's pretty cool. So, and and So you can see like basically if I have take a values here, let's say take a value here, take this value as an example. What's AX or the inner product of AX? So let's assume A is normalized. So let's say the vector here, the norm here is equal to 1, or like the norm will be like just the inner product of itself is equal to 1, or like you can think of like A sum of AI square is equal to 1. Now then AX will be just the projection. So I have
Dr. Cheng?
Yes.
X is the data points, right?
Yes, as X is a data point. Yeah.
Okay.
In particular here, like consider this X, say for example, this X. So for this X here, AX will be, okay, maybe I give some precise values. I see if it give more intuition. Let's say I have this A here is, yeah, okay, let's forget it because that would be more complicated. So AX here, if you remember, like vector calculus or geometry, or like maybe just geometry, I guess AX here is actually just the projection of this X vector. I can write this. Let's say this is the X vector here. This is the X vector here. And AX will be just the projection on this A vector. So this is the A direction here again. Like this is A, right? So this would be AX, right? So if I take this as origin, so so therefore what? Like maybe okay. Let me just make sure you understand following like what I'm doing. So let's say I have this one point is x1 here. There's another point here that is x2 here. Let's say. So I compare with like ax1 and ax2. So is ax1 bigger than ax2 or like smaller than ax2? Bigger or smaller? Yes, it's bigger. So this is the direction because this is a projection, right? Projection into this A direction. So AX1 will be okay, getting bigger along this direction here. Actually, AX1 probably will have this value is AX1, right? AX1 here. So maybe AX1 is 4, let's say. And then AX2 here, if I draw here, let's say. Actually, AX2 maybe is about like 0 or something like that, or like minus. So AX2 will be like different color here. So this very tiny value here, maybe minus 0.5, I don't know. So you see my point. So now then like maybe I here like instead of like dot, let me use cos like for the data point again. Let me rewrite this as cos. It's easier to read. Now, so then like, if you look at like logistic regression, what it's doing is I just, okay, I find this A and trying to separate these two sets here, right? Two two sets of points here, or two sets of sample here, two sets of inputs here, whatever in this visual space here. And I basically just look for this A, right? This is a one possible A is going to separate these two guys here. Now let's see another. Okay, maybe I missed something first. I here apparently I need to have a bias, right? Because in this case, I want to have, if I look at, I consider the logistic function, the boundary between these two sets will be when AX is equal to 0, right? So in this case here, like AX equal to 0 is here, is probably not the boundary I want, but instead, like I probably want to take the threshold, maybe like here is maybe AX equal to 1, right? So I want to, in this particular case, probably let's say this here is a AX equal to 1. So actually I want to have like a classifier. I have a simple classifier will be like AX, if it's a bigger than 1, then I will classify as cat, right? And it's like less than 1, will be classified or not a cat here, right? So, but remember, like often like, we just plug in a dummy variable here, like I mean, in the sense I have x extend one more dimension into x1, and then I have a, instead of just a, I have a and have a b here as the bias. So then it will be, that bias will be this one here basically, or yeah, so it's like here, or like maybe it's like minus b instead. So, but here, let's consider like for SVM, like let's consider the bias explicitly. We have this bias here, also like this B here. I think it's not very important, but just a remark here. I guess because for my let's see, yeah, for my notes here, like for this part, like for the SVM, I did explicitly put down the bias. So so in this case, we have that. There's a bias to shift the sigma function here. What I mean is maybe I should wait clearly that I have the decision is say something like ax plus b, something like that, to decide whether it's a cat or not a cat. Now, okay, let's this is for one A, right? Now, if I consider another A, maybe like A tutor in this direction here, A tutor. Now, then I can have like another kind of separating these two. Okay, this is kind of okay. Now, I hope it's clear, but I'm not sure. It's like because it's like the drawing is a little bit bad. Maybe let me emphasize the data points here. The data points here. I have a data point here, 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 here. For the cat samples, and then I have like non-cat sample is like here, 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 so on and so forth. No, now let's have another question here. So is A tutor better than A, or like A tutor is worse, or like A better than A tutor? So when I mean better, it's like literally like as a classifier. I have a classifier here that I can have like basically classify the cat and non-cat class with this AX plus B, and then have compute this sigma to determine whether it's a cat or not cat, right? Or I can have like A tutor X plus, I probably have a different bias like B tutor here. And so, yeah, which one is better? Yes, A tutor will be better, right? Better in the sense if you think of that. Okay, both of them, like for these data points, for the given data points here, like for this data point here, and this data point here, both of them I'm able to like kind of split or like kind of like, yeah, to separate the two data sets here. But for if you think of like this data point, like potentially can have error, yeah, or like you may have like more data points. It's for the first separation, like using A, it's more likely that you have data point that go outside to the other. I mean, to out from one side across the boundary to the other side, right? Than for this guy here, for the second A tutor here, and this is basically exactly the idea of like SVM. So SVM is actually exactly solving the same thing as logistic regression. For logistic regression, we're trying to like optimize this A here, right? For given X, if you remember, like we have like all this training data. So I have like A, essentially I have this for training data like A, X, I, like all the training data plus B, right? So sigma of them, I want to make sure that, okay, let's see. I can have like, what's the error essentially? Like if xi, let's say like for xi input, like I have like yi is represent a label, and more precisely I will have like yi either 1 or -1. So if yi is 1, then means that like that point xi is a cat. If yi is -1, then it means that the xi input is not a cat. So then if I have good representation, if okay, actually that's also yeah, that is for SV I'm going to do, but so for yeah, okay, this yeah, actually this is still fine. So then what I want to do is yeah, actually I'm sorry about that. For logistic regression, I probably need label like COM1 because I say here it's like COM1 here. Uh wait a sec. I don't want to confuse you afterward. Let's do not call this yi here. Let's call this ci here. The ci is labeled like 1 and 0. I will have yi later on that I will use label like 1 and -1. But if I consider logistic regression, I want to minimize this way. I want to have my sigma here will be close to the actual label, so I can minimize this maybe a square difference of that and sum over all of them. Like maybe I have like n data points, and I'm trying to look for A to minimize this function, right? Basically, so I minimize this over A, right? That's exactly what logistic regression is doing. And so for SVM, on the other hand, is like I want to, I'm not solving this, but instead like I try to maximize the margin. The margin in the sense I call this margin will be like, for example, like for A tutor, the margin will be something like that. The distance, the maximum distance between, or like the gap between like the two set of data point for that particular A. So I have like A tutor, the gap will be this big, right? But on the other hand, for A, my gap will be only that big, right? So I have A, the gap will be more or less, oops, that's fair. So this will be the gap, right? For A. So apparently, like for A tutor, like the gap is larger, therefore it's better. So is that all clear? The high level idea what SVM is trying to solve? It's just basically I look for the A, or like A tilde in this case, look for the A, then maximize the gap to separate the data set. So
Yeah, the high level is clear.
Yeah, high level is clear, then we can go into the math there. So let me, I think I copy one image from the slide. So I have here, I instead use A, I use W here, like in the slide. Okay, it's okay. Like in the slides, I use W. Let's use W now. And basically, this is a redrawing what we have there, right? So we have W is along this direction. So then I have basically, let's say W itself is not normalized. Then I have like W over W. This is normalized. Or like this can be our A earlier. A is normalized, right? Remember, like A is equal to 1. And like W itself, it doesn't necessarily to be 1. So I have W, the inner product is equal to W, the norm here. So therefore, if I have AA, then this is actually equal to W. Sorry, I should have a square here. So therefore, give me W over. Actually, wait, it's actually should be square here, not. Yeah, square here. So therefore, I have W, and so it's 1. Yeah, that's nice. Yeah, so it's, yeah. And so it's basically just normalize W, right? So then I will say, like, for this guy here, okay, if I have a point here, X1 here, I have like AX1. This will be I always confuse myself. Wait a sec. So let's try to find the gap. So the gap here should be, the distance here should be, this should be like A, let me start from like this. So I have like I start with like, let's say I start with like AX. Okay. I decided what was the best way to approach this. So along this line here, the AX will be the same way. The all AX value is the same. Let's say, call this like AX value is maybe B1. Hopefully it's okay. And this value is maybe C1. Let's see, C1, and this is a C2. Let's say. So, and then like, so therefore, like I will have like AX1 is equal to C1, right? And then like AX2 is equal to C2, right? And by the way, I can shift the center of C1 and C2 by something such that like this will be, let's say this is D. Let's say this is D here. I can shift by something such that like AX1 is equal to D Okay. This okay. So I can shift by D here, so that like I have like A x1 minus D. That's basically here. Plus D is equal to C1. I'm basically doing nothing here. From here, this is like just what we assume like that. I have like AX1, AX2 is like equal to C1 and C2, right? So I'm let's say I just say like take D, or like take the gap here, so the distance is 2D. And so therefore like I just add D or minus D or something like that. And then I have also AX2 minus D plus D is equal to C2, right? So, but then I can shift this C1 and C2 and D1 and, I mean, shift the D on the other side, basically move the D on the other side. I have like this way. So now I'm getting much similar to this guy here. And, but there's and actually this will be minus D if I have this thing here. So, but then like, by the way, like, wait a sec. I'm okay. Yeah, I'm sorry. Like, this is D, but the shift should not be D actually. Let me shift by, I want this to be like plus D and this would be minus D. So let me shift by something else. Let's shift by S, let's say. Yeah, okay, that should work. So you see, let me repeat again. So from our discussion earlier, so along this line, the whole thing, if I do a dot product with x1 will give me c1, right? And along this line will be give me c2, right? Now I want to shift the center, so I will add some bias here. Let's say add subtract s here, such that like after I subtract s, like this will shift to plus. Actually, it shouldn't be plus d yet. Like will be like this value, these two values will be the same. Let's say this is equal to maybe f, like maybe g, I don't know. So and this is like minus g, you know. So it's so that's good. So I basically I want to match with these two function here. So and then I can normalize this to 1 and minus 1, right? So I can divide this by g here. So if I divide it by g for both sides, so I have like minus 1 equal to 1. I have like s minus over g and a x1 over g here. Actually, it turns out like my g is better to just call it w here. It's actually the g is actually w here. So I can have like this is actually equal to w here. It's minus w here. So if I divide it by that, actually, I have this is a over g here, x2 minus s over g is equal to minus 1, something like that. And now what's actually the distance? The distance Yeah, actually, I think like it should be much simpler than I thought. Like why I'm getting like kind of a little bit confused myself. So let me go directly to the slides. Okay, it's getting um. So so basically maybe I start from here. Like you see, like I can always shift like whatever I'm trying doing. Is like I can make this line along this line here satisfy this equation, right? And then along this line will satisfy this equation here. Now, and W, by the way, like the wait, actually my okay, I want to make it not enough coffee today, I guess. Let me go back to here. Actually, this is actually when I go back to here, the gap here has already got the gap. Okay, I think I'm kind of like elaborate more than I need. Yeah. So actually, yeah. Sorry for the confusion here. So when I start from here, when I have this here, I already know what's the gap. Actually, seriously, why I'm not even sure why I'm elaborating all this. So the gap is what? It's basically should be just like C1 minus C2, right? This would be the gap, right? Yeah. Okay. I don't know why I was just stupid. So, do you guys agree with me? I'm kind of like following.
Yeah, that makes sense.
Yeah, that's just C1 minus C2, right? So
Yep.
what's C1 minus C2 now? It's just a okay AX1. By the way, I have A is equal to this guy, right? So therefore it's equal to A AX1 minus AX2. Yeah, okay. AX1 minus AX2 anyway. AX1 minus AX2. But A is equal to W over W, the ln of W, right? Minus a W minus W ln of W2. So this is the gap equal to that. Now then I can pull W1 out, right? So 1 over W out. I'm sorry, 1 over W out. So I have W x1 minus W x2. But by the way, like I have Wx1 is equal to 1 plus b, right? And Wx2 is equal to minus 1 plus b, right? So it's like 1 plus b minus 1 plus b. I have b got cancelled. So therefore, like it's just equal to 2 over w. Yeah. So yeah, so sorry for the digression. I didn't need all this actually. So yeah. So therefore, like the gap is just like this. So therefore, I should just maximize this 2 over w. And but what do I want? Like there's some constraint here, right? I want to make sure that now if I have labels, now I use yi instead of xi. For each of the labels, I have yi is equal to 1 and minus 1. I would say that all this label for the cat size is 1, and all the labels on the not cat size is minus 1. So then I can, if I can make sure that yi multiplied by, let's see, wx minus 1 is bigger than 1, then would be okay, right? So because this is like the place you have, this is like, for example, if I consider like on this side here, like all xi will be, if like for everything like go above this line, I will have like wxi minus b will be larger than equal to 1, right? And on this side, the label is 1. Yeah, so therefore like this should be satisfied. Now on the other side will be the same case, right? So for everything like on this side, we'll have wx minus b will be less than equal to minus 1. So if I multiply by this label is supposed to be minus 1. So minus multiplied by minus will be plus. So it will be like, should be bigger than equal to 1 instead. Also. So now, so is that clear? So therefore, I will have essentially this optimization problem coming up. So it's like I trying to make sure the constraint is satisfied. It's like I have all the points here is go beyond the margin, right? And I want to maximize the gap here is like basically 2 over W. And of course, equivalently, like maximizing 2 over W would be the same as maximizing just W, or like maximizing W square.
So it's clear. I'm just curious.
Yeah.
Is this like an ideal case where we have these two widely separated?
Oh yes.
Groups?
I start with this for elaboration, for easy exposition. So you will see later on we can have a soft margin case. Basically, if we have points like actually go on the other side, that would be considered some
Yeah.
kind of outlier. Then in that case, I will use a soft margin SVM. Actually, in most cases, we'll use a soft margin SVM anyway. But it's
Okay.
good to start with like the discussion with hard margin. It's easier to explain.
Great.
So with that, like then like basically we would like to solve this optimization problem, right? So I will have now like a quick maybe a explanation of kind of like, so optimization. So let's say let's consider like a general problem here. Let's say fx, and I have like such that like also like gx is like bigger than equal to 0, let's say, or like bigger than equal to some value like g0. So do you guys know how to have any experience solving optimization problem like this before? So that's a keyword for that, like a couple keywords. Like, do you?
No, Professor.
Yeah. Uh, yeah. Lagrange multiplier. Do anyone heard of that?
Yeah, I've heard of it, but
Yes.
Yes.
I think I need the review.
Okay, that's fine. It's actually very easy. So you see like it's actually very obvious. But if basically if you get to a unconstrained problem, if I don't have a constraint, then you know that like by kind of like your first class in calculus, then I can just take the derivative of this guy, or like in this case, if x is a vector, then you want to set the gradient to be 0, right? Something like that. Now with this constraint, let's say if I have the constraint like this. So what I can do is let's think of let's think of it this way. So if I consider a different function, instead of this fx, I consider, let's say, a L function of Lx lambda is equal to fx minus, let's say, I need to make sure the sign is right. Maybe I'm not, but let's see if it is right. Let's see. Oh, okay. Let's use minimize, like we are solving minimization problem. Let's use minimize. Yes. Maybe the size like that. G is actually this other size, right? So okay, that's fine. So it's okay. Like you just need to understand the concept. Like what you're seeing here. I don't remember stuff. I rarely memorize stuff. But if you understand the concept, you can figure that out yourself. So like let's try this out. One minute say I'll introduce a Lagrange fun like Lagrange function, I guess maybe call it. So such that is I introduce a new variables here and I add this guy. And if I consider like a different optimization problem, let's say I have minimized x and then maximize lambda, this L lambda x. So I move this guy down here. So I'm basically arguing these two optimization function optimization problems actually identical. So now why so? Now think of that like I need to have this constraint, right? I want to have this constraint gx is bigger than equal to 0. And okay, I missed something. I need to enforce also lambda is bigger than equal to 0. So I force a lambda bigger than equal to 0. So now if this is violate, let's say if this is I have like G0 is less than Gx here, if this is violate, then this value will be negative, right? Where G0 is bigger than then I probably should have a positive sign, I say. Oh no, actually it's okay. It's okay. Okay, that's okay. So if this condition is violate, then this will be negative, right? Now what's the maximum value for this guy here now? Or like maybe I should say, if I just look at this part here, what's the value for this thing here? If this is violate. So okay, this is a question here. Not the entire thing, just this part, just the maximum here. You ignore this minimum here, just this part here. No, that this is maximized, this is minimized. This is like optimized in two different direction here.
Which one did you ask for, Max?
This inside the bracket. So if this is violate, G0 is less than Gx, what will be the things inside this bracket here? Okay, be careful. Like look really carefully. If this is violate, this is minus negative, right? So what is lambda here? So lambda can be anything bigger than equal to 0. So yes, it should be infinity, right? So be very careful. Like if this is violate, right? If this violate, this is negative. This is a minus something. I don't know minus what. And this is minus sign also, right? So therefore, you see, I play with these sign things here, like here and there. I never remember that. I never remember. But you're able to figure that out, right? So I want this actually to be infinity. So if when the condition is violate, so when this is minus, so this minus this part is positive, right? So lambda can be anything as long as positive. So therefore, like this would be infinity, right? So you see like, okay, that means that I have like these things, maybe I call this, actually I call this f here as a function of lambda here, or the f as an x here. Oh, no, I already use f, I'm sorry. Maybe I call this h here, hx here. You can see that the hx here is actually equal to infinity with g0 is less than gx, right? So now if g0 is bigger than gx, what do I have? What's this thing? Yes. So if I have like this is satisfied, basically the constraint is satisfied, then this part now will be negative, right? This part is positive. So with the minus sign here will be negative. So I want to maximize this thing here, right? The best thing I can do to maximize this would be I just set lambda equal to 0, right? So therefore, then it will just get me back just equal to fx. And so then you can see that like actually I'm absorbing like by introducing like this part here. Now I would calculate, maybe I erase some of this. Maybe I rewrite this. So minus lambda g x minus g0. So by introducing this part, we are kind of absorbing the constraint, this here, into the objective function there. And this lambda here is known as a Lagrange multiplier, basically. So actually, you can argue like in the same way. For example, if you shift the sign, if you have like this less than equal instead, then probably like this will be flipped and stuff like that. So if I never remember like how it actually works, but you can argue about that. And also like you can deal with equality constraint as well. If you this have equality constraint, then I can have just this maximize instead of like have like lambda bigger than equal to 0, I'll just have like lambda like can be anything. Then again, like, you can argue the same way that like unless this is equal, this is satisfied, then I always have this part is equal to infinity. Oh, by the way, like this is equal to infinity, therefore it won't be you won't I mean in terms of the entire optimization function, right, this will not be pulled out, right? Because why we want to make it infinity, because remember like we are trying to afterwards trying to minimize over x, right? So when I basically if I write like that again, like minimize hx here, so because when the constraint is not satisfied, is equal to infinity, so I will never pick up the x such that this constraint is not satisfied, right? Or like I should say this constraint is violated, right? So I hope it's kind of clear. I mean, this is actually is the conceptual is very simple, but as you see, like I will stumble always, like whether the sign is like should be plus or negative, like this should be plus or like bigger than equal to 0 or less than equal to 0. But that's actually minor. You as long as you understand the concept, you can figure it out always. So now I have this now, like I can use a Lagrange multiplier. Then for the problem that we have earlier, we can introduce the Lagrange multiplier. So remember, we have the constraints. We do not have just one constraint. Actually, we have multiple constraints here. Let me make sure I put the chart box right down here. So remember here that we have the optimization function like this, right? Minimize W square such that this is for OI, for each of the data point there's a constraint. So therefore, we don't have like one Lagrange multiplier. We have like many of them. So then I have like sum over all the Lagrange multiplier alpha I here, and I basically, this is my gx earlier, and this is my g0, kind of like, and this is my fx earlier, right? So then I will have like for all of this alpha I supposed to be bigger than equal to 0. Now, typically, people don't solve this problem directly. After drawing this, it's not very useful unless we allow ourselves to flip the two optimization function, optimization operator here. So instead of like doing maximize and then minimize, let's swap that. Like, let's try to minimize first and then maximize. Okay, by the way, like does it always okay to do that? Okay, let me give another question here. Do you expect like this is bigger than equal to this, less than equal to this, or like equal? In general, like it should be. You see my question again, like, so if I have, this is my original optimization problem, right? So we just said like we have these constraints there, then we absorb into that like by introducing a Lagrange multiplier added to the objective function, and then introduce a additional optimization operation like first maximize over alpha I here. Now I swap the order of the maximization and minimization. So my question is like in general, like should this new problem, right, typically people call it dual problem. The dual problem and by the way, this is often known as the primal problem. So of course, after the optimization, you get some values, right? You optimize that, you get some value here. There's some solution, like maybe equal to C0, and this is a C1. So will C0 be bigger than this? Which one will be bigger in general?
Well, I see the answer there on the slide, but
Yes. Okay. I put the slide. Okay.
but I don't see it in the. I don't see how
Yeah.
that's the case. I don't.
Yeah, I guess this like need to be. I guess I will leave you guys to think about that. Like it's actually not hard, but the easiest things you can do is like do a discrete case yourself, like to argue yourself. Like for example, I have a discrete case here. So maybe let's don't make so many numbers here. Maybe just like 1, 2, 1, 3, 1, 2, 4, 3, 1. I don't know. I'm not sure what. Let's say I do minimization this side and do maximization this side here. So if I first do minimization first, I get what 1, 1, 1 here, right? And then I do maximization, I get like the maximum value is 1. That's basically the second case here, right? The second case here. Now, if I do maximization first, I will have like 4, 2, 2, right? And then I do minimization, we get 2.
Okay, that's very helpful. Thank you.
Yeah. So yeah, of course you can actually prove that like yourself, like it's possible to. Yeah, it's actually not difficult to prove. I'm not sure. Maybe I put in homework. I don't know. Maybe not. But yeah. So but yeah, just to argue yourself like that. So but I mean, for some cases, like for example, like if your problem like to start with your fx is converse, like I'm not going to like converse optimization so, but then like these two problem will have like the same value. So C1 will be C0. Actually, the C in this case, as we said, like C0 in general is bigger than C1, right? So have C0 minus C1 is known as this duality gap. So, and if you Google like a duality gap, you will get lots of like things to talk about that. And the duality gap, when there's also condition when the duality gap will be 0. So it will be 0 when one condition will be like, one possible condition will be like your original function is convex and so on. So in our case, actually, the duality gap it will be 0. Okay, here is a little bit, let me erase some of these things here, will be like easier to see. So now after we swap this minimization, optimization, maximization, the nice thing is that like the minimization here is unconstrained, right? So therefore we can solve this part like using just like what we learn like in kind of like the first class in calculus, just do a gradient of like W and then try to solve this guy, right? And also of course I dealt with two variables here. I want like gradient of this L is equal to 0 and gradient over B also equal to 0, something like that. And of course, I have other constraints basically, like alpha I should be bigger than equal to 0. That's we need to make sure. And note that there's one more constraint. It's known as this complementary slackless conditions. I mean the constraint for your final solution, it will be something like for each of the Lagrange multiplier, or maybe I go back to this slide here. For this Lagrange multiplier, this term like added to the original objective function, if you have the final optimum value, let's say I have the final optimum x star and lambda star, then I will have this value here, lambda star gx star minus g0 is equal to 0. This will be equal to 0. So this is like quite easy to understand just from like how we build, I mean, the Lagrange multiplier and how we build the objective function. Because remember that like from here at the beginning, we say that, let's see. We say that like when the constraint is violate, then basically, oh, wait. Constraint violate, I don't care basically. If the constraint is not violate, basically if I have like gx is bigger than g0, right? G is bigger than g0. Then you look at this here, the optimization function here. For gx is bigger than g0, what's the maximum value for this, or like what is the solution for this optimization function? Will be like lambda is equal to 0, right? Because when this is positive, I want to maximize that. Of course, I would want this lambda equal to 0, right? And if this guy is okay, should I slow down a little bit? I tend to confuse a lot myself, like here also. So the complementary slacker constitution is saying that for this term here, if you have the optimum value for your lambda and x star there, this term here should be equal to 0. And it's very easy to understand why, because let's say if this part is non-zero, because from the first optimization problem here, if this part is non-zero, then to maximize these guys, I would have to force lambda equal to 0. So therefore, like the whole thing will be equal to 0. And if this part like is already 0, then like, of course, I mean, if gx minus g0 is already 0, then of course the whole thing will be 0 as well. So therefore, like either case, like this thing will be equal to 0. So is that clear? So it's long like the complementary slackless condition. So therefore, in this case, like this part here is actually is always equal to 0. I mean, always equal to 0 meaning that like for the final solution, I have this W star, like B star, and X star there. Sorry, there's no X star, sorry. Alpha star there. I should have like this part is always equal to 0. This will be useful like as we solve the problem. And let's see. I'm not sure I should go step by step or to write this up, or so maybe not. I guess you can try it at home. It's not difficult. So now here, as I said, like if we after we swap the maximization and minimization, I want to find, let's solve this first part first, like with the minimization first. Then we just say take the gradient of this function L with respect to W and with B, and then set it to 0. So if I take the gradient with respect to W, what do I get? So I get here is kind of like take gradient. If you remember, like we did it last time, like W square, take the gradient, we'll get just W, 2W. So over 2, I get W here. I take gradient of this guy here. So remember, I take gradient with respect to W. So anything without W will be all equal to 0. So only with this term here. So I take W, actually I should get Xi back, right? So therefore I should have like something like this, like minus alpha I, Yi, Xi equal to 0. And that's what we have, right? This is equal to 0. Then I move the other side. I have like this one here. Now I can do the same thing for B. I should get this, or actually it's be pretty simple. Let's look at this anyway. Like if I take derivative with respect to B, we'll get what? This get 1 here, and I get let's see, alpha I Yi multiplied by B, right? So I have like I alpha I Yi, right? Minus 1 is equal to 0. Wait. Oh, no. What okay, I get confused myself. So I take derivative with respect to B here. The only term with B is like this one multiplied by this, right? I take derivative of B is just equal to this guy here. So it's just equal to this one, right? This one set to 0 will be just equal to that. So now, actually, you can plug this back into this equation here. So if I plug back W is equal to alpha I, Yi, Xi, right? I plug back into this guy here. So actually, like you have a 1/2 here. You can see that this is actually the same term as this guy here. And so you subtract that, you have like 1/2 back of this thing. And then like I also have like this part is equal to 0, right? So we have like derivative equal with B is equal to 0. So therefore, like this part will be gone. So I will just have like something like I still have a 1 here. So I have like, so therefore I should get something like this, as you can see. Have this like this. So don't worry about it. It's just algebra. Actually, if you lost a little bit, like yeah, it's the the most important part is like you know how to take the derivative you need to, like how to compute the gradient. But if here like you're a bit, I mean, not following, I mean, yeah, I think you can go back to try it out yourself. Like that's actually better. Um, so let's see. Yeah, so I have essentially like this original objective function will become this guy, right? So as I said, like, it will become this guy. So this one, after you try to compute the gradient with respect to W and gradient with respect to B set to 0 and substitute back into this one here, you basically get this here. And at the same time, like when take gradient with respect to B, we have this way. So I need to put that constraint back. So I have a new problem, a different problem now. The dual problem is I reduce into this form here. So it looks complicated, but actually it's easier to solve here. This problem is like quite quite conveniently solved. That's why like support vector machine was so popular a decade or two ago, because like this is can be solved very computationally effectively. It may not be obvious, but I guess I can give some intuition. I won't go into detail. So the intuition is that if you look at this, we're solving for alpha, right? But this thing here, what is that? Like this is essentially just a quadratic equation of alphas, right? So it's just like sum over like all the linear term of alpha and then this product term of alpha. It's really a quadratic equation. It's nothing. It's just a quadratic equation. And you know that quadratic equation can be solved with closed form, right? So what we can do is like, of course, like we have additional constraint like this, but what we can do is like we can fix, let's say if I have like n alphas here, so I can fix like n minus 2 of them. And then because I cannot fix n minus 1 of them because that's one additional constraint, right? If I fix n minus 2 of them and add this equation, then I will become like just one variable left behind is free to move around. Then this problem itself like become a completely quadratic equation. Then you can solve like with closed form. Then you can find one alpha, maybe like alpha one. What I mean is like maybe I fix everything except alpha 0 and alpha 1. Now then I can solve in closed form just like one line of code. Then you get the optimum alpha 0 and alpha 1. Now then you can move to another pairs and repeat that like many times. Then you eventually get the optimum alphas. So any question? So once we solve for this alpha, then we can go back because what's W now? We know what we care. We forgot like okay, we may be lost like after all this. Remember like what we trying to do is just trying to compute Wx, right? Wx, and then determine whether it's like W is minus B is a positive or negative. Is positive, then it's a cat. If negative, it's not a cat, right? So we need to find W and B basically. Now, after I solve for alpha, I know what is W, right? Because I have this earlier that W is just equal to this guy, right? And also like one thing, remember why we actually that's one thing like why I like to brought out the complementary slackless condition here. Remember that we just mentioned this complementary slackless condition. This will be always equal to 0, right? And by the way, maybe one last question or something like that. What is the condition that this is equal to? I don't know whether I should. Okay, maybe like this. This wait a sec. Oh, okay. That's fine. Actually, yeah, I that's okay. We remember this guy here, this condition, or like this y I minus x I w. Oh, okay. How do I? So know that like I have like yi, let's write it down again, like xi minus b, this guy minus 1, right? I have this thing here. That's the condition is going to multiply by my Lagrange multiplier, alpha I there. So now okay, let me give it probably not a very obvious question, but I will see if you can answer that. So let's consider this point, these 2 points here. Just give you this is a point, maybe like x1. I say this is a x2. So I would say one of the alpha is equal to 0. So that's corresponding alpha 1 and alpha 2, right? So I give you a hint that one of them will be equal to 0. Alpha 1 equal to 0 or like alpha 2 equal to 0. Remember that like we have the complementary slackless condition saying that this whole thing is equal to 0. Okay, so you guys, some guys follow the majority, but like it's not always the majority is correct. So let's think of like what was this condition here. At this line here, I have like wx minus b will be equal to 1, right? So I'm the label here on this side actually y1 is equal to 1, right? So here actually I will have this part is equal to 0. On the other hand, like for here, I will have wx minus b will not be equal to minus 1. Actually, will be like less than minus 1. Definitely less than minus 1. And so multiply by y. Sorry, this is a 2 here, right? I say 2. Multiply y2. Y2 is actually equal to minus 1 here. This guy will be bigger than 1. So therefore, like this guy minus 1, this thing like y2 wx2 minus 1 minus b minus 1 will not be 0. So definitely not 0. So by complementary static condition, So this guy is non-zero, that this one has to false to be zero. Actually, I cannot tell whether this is zero or not, but I can definitely tell that like alpha 2 is equal to zero. Alpha most likely is non-zero. Actually, alpha not supposed to be zero actually. But alpha 2 definitely will be zero. So then you can see like it's actually most of the points here, alphas will be equal to zero, right? Because everything only on the boundary will be non-zero. And that's what we call the support vector, basically. Those like on the, well, that's why they call it support vector machine. Okay, I'm going over time actually. I probably can stop here. Should stop here. But let's continue next time then. I will stay for 5 minutes or so, like let this on, like in case you guys have any questions.
Well,
Yes.
I have a question about the
Yes.
homework.
Okay.
The second problem is, well, if anyone has a question about the material, I guess
Yeah.
maybe they can ask that first.
Yes, sure. Yeah.
But if not,
Yeah. You can definitely.
okay. Well, so the second problem is the one where you have us taking the gradient of the quadratic form, but you
yes, I think-
asked to do it with respect to the matrix. And
Yes.
I'm having trouble I've always kind of had trouble with these abstract vector
Yes.
spaces, matrix spaces, and for the gradient of like just a regular vector space, I get that. That makes sense to me how you explained it with the vector pointing up the greatest
Yeah.
slope, right?
Yes.
But when we're doing it with respect to the matrix, I can't really wrap my head around what that should be. I know you said that the gradient should be the same dimension of the.
Yes. So therefore, actually, your gradient will be a matrix as well. So
I thought that might be the case. Yeah.
it get beyond of like usually people talk about vector calculus. So, but you can always think of a matrix as just a kind of like a vectorized array, but you kind of like pack into a two-dimensional object, right? So yeah, the if you think of that way, like yeah, your gradient will be the same, because I actually uh even though like you have a matrix, right? You have a matrix,
Yeah.
and you think of like a function of a matrix, so of a function of a matrix, and then like the gradient of this function with respect to this matrix will be saying that like if I modify this input, like in what way it will get me the largest value, right? So I have this as a is m here. So what is that? So therefore my gradient fm is something like, how do I modify this guy, modify this m such that like I'll get to the largest f basically. So in that sense, this gradient here, it should be like same dimension as this guy as well. Yeah.
Mm-hmm.
Yes. Yeah.
So
yes.
okay.
Yeah, but you can always like just decompose into like elements. So let's say if I have like f, I have like this as a matrix, or maybe like just 2 by 2, like matrix is 2 by 2. So then the gradient of f will be basically just equal to the partial derivative of f with respect to m11 and partial f m12, partial f m21, and partial, partial f
Okay.
m22. Yeah, it's just like that actually.
Very good.
Yes.
Thank you.
Yes. So any other questions? So
Professor, my internet was being a little laggy, so initially the start of class I couldn't hear you properly. Did you give any instructions or anything in the first like 10 minutes of the class? anything? Did you say anything important other than the material?
Sorry, I didn't get the question. You mean today's
Uh,
class or like in general?
yes, Professor. Today's class, because I couldn't properly hear the first 10 minutes because my internet was causing an
Oh,
issue.
okay.
So, did you give any instruction, anything in particular, which like other than the material? Because material, I can always watch the
Oh
video, but
no,
any
I did,
instruction?
yeah, I didn't actually, and yeah, and if in general, like if I have something like that, I probably would record it as well. So along with my recording, so don't worry about that. If you miss the first 5 minutes or something like that, you can go back to look at the recording. Yeah,
Okay,
yeah,
Professor. Yeah,
yeah,
thank you so much.
yes. So I guess if there's no questions like that, I will see you guys on Thursday then. Yeah,
Thank you.
yes,
Thank you, Professor.
yeah. See you guys.